Okay, good morning all of you. My screen is visible.
Yes, sure.
Okay, we'll see this first unit, the power semi switching devices. In this, it is very small unit. It will take hardly 4 hours or maximum 5 hours. In this, we discussed about the power diode. I told no there is a difference between general diode and power diode. So we will look into that. And there is a topics will be like this: power diode, in that VI characteristics, recovery characteristics, and types of power diode, that is a general purpose diodes, and then fast recovery diode and their applications, and power BJT. This also we need to see the basic structure, working, steady state, and then switching characteristics. And then MOSFET, this will be the same concept whatever we discussed in BJT, and the MOSFET also we need to discuss. And power IGBT, this is the advantage of BJT and MOSFET combined together will form as a IGBT. So there is a individual drawbacks are there in the both devices, BJT and MOSFET, and we'll consider only the advantage portion that will make use in that device, that will become as a IGBT, insulated gate bipolar transistor. And then gate rise. Another one is a comparison of the devices. So these are the small topics, very small topics. So comparison means we use the BJT, MOSFET, IGBT and their applications. All the three comparisons we'll look into. Another one comparison also we'll see, diode, ordinary diode and then power diode. So that also one of the comparison. This is the complete syllabus in that first unit, and after completion of this we'll move on to third unit. Then our second unit is completed. Third unit is very simple. Single phase controller and then three phase controller. At least we'll try to complete half of the syllabus of the third unit, so that will be the total half will be completed subject itself. Now we'll see the overview of our semiconductor switches. Here, all the devices, whatever device we are going to use or discussed, that will be our purpose is to use as a switch, not whatever we may be discussed in the electronic subjects and all. There may be saturation mode, active mode, cutoff mode, like that. We used here only as a switch. There is a two operating modes. Either it has to be on completely or it has to be off completely. That is only the thing here. So it like a switch. When the device is on, the contacts will be closed, and if it is open, then contacts will be, means switch off, contact will be open. Only thing is how the device is going to switched on or switched off. So that is only our process to know, because the different devices may have their different characteristics, like a BJT or a SCR. We noticed one thing in the case of SCR also. Once the device is gate pulse is given, then automatically device will on, means switch will be closed. Similarly, in case of BJT also, once current is passed through the gate, here gate means base of the device, then the device is going to be on. And if you remove the base current, device will be open. So that is the difference. Either device has to be on or off based on the gate base current. If base current is given, switch will be closed. If we remove the gate current, base current, switch will be open. But whereas in case of other devices like MOSFET and IGBT and all, if we give voltage, gate voltage, then the device will be closed, and if you remove the gate, device will be open. So like that, but whereas in SCR is not so. Once if you give the gate current, it will be on, but you cannot be turn off by make use of the gate like that, because that is only when you reduce the current pass through the device zero level or below the holding, then only device will be turn off, otherwise it won't be. Like that, we have different devices with different strategies. We'll see one by one, and end of that we'll compare all the devices. Some devices will suit for some application, and some other devices will maybe suit some other different application. Like that depends on their rating. Some devices may be higher rating, some may be lower rating. Like that, we have as a different strategies. So that is the reason we can able to process this. Now we can see that introduction. There is a power semiconductor device can be classified in three groups according to they. You can see that what you call it as a groups. Three groups we have. One is a degree of the controllability. I don't know, the controllability will differ. Thyristor is different, BJT is different, MOSFET is different. Like that, we have different strategies. That's why we divided. Diode, you can see that on and off states controlled by the power circuit. It is very straightforward. Nothing is required for gate and all. Simply, if you give the power, supply is connected to the diode. If it is a anode is connected to positive, then it will be conduct directly. So that means, and if you remove that, that is going to be off. So in that case, we can say that there is a controlled by the power circuit. If the anode is positive or not, it will be controlled. Now, thyristor, you can see that latched on by a control signal, but they turn off by the power circuit. So that means to turn on, we used as a control signal. What is the control signal here? Gate. If you pass the gate current, two ways, or I can say that three ways also. So you can, because of turn on methods we have based on that, you can pass the gate current up to IG minimum, it will trigger, or you can pass the voltage across gate and cathode, then also device will turn on, or you can give the gate pulse, then also device is going to be on. So that means whatever may be the means, you need to control the device only in the on state, means at what instant device is going to be turned on, that will be decided by the control signal. Once if you pass the gate signal, automatically device is going to be turn on. That the device is waiting for the gate signal. So that is all about in our control. Now once the device is on, you don't have any control over the device. So that is the reason we need as a some forced commutation circuit. If it is a DC is input, or it is a natural commutation, DC input is a AC supply, like that. So that means off process is controlled by the power circuit based on your input. You can decide at the off, but on only you can able to control. Another one is a controllable switches turn on and turn off by the control signal. So that is the device like MOSFET and IGBT and all. Both is in our control. You just give the voltage, gate voltage, it will be turn on, and remove the gate voltage, it will be turn off. So that is all the controllable switches. Now, controllable switches include BJT, MOSFET, GTO. BJT also same. If you pass the base current, it will be turn on. Remove the base current, it will be turn off, like that. So these are the some of the devices are the controllable switch category: BJT, MOSFET, GTO, gate turn off device, and IGBT. So these are the devices. I think you don't have the GTO concept, but it is very simple latest device. We can easily turn off the device by make use of a gate turn off the device. So that these are the controllable switches. Now work as a switch and low power analogy or digital circuit control them. So it is, I don't know, whatever may be the device we are using in this power electronic semiconductor devices are a switch only. It acts as a switch only. When device conducts, then it behaves ordinary contact, like whether is a thyristor or a MOSFET, irrespective of the device. Once the device is closed, means it is turned on, now it is simply like a contact. So between the source and load, means switch will be closed. That is only the mechanism here. So ideally, no voltage drop appear across the device. Once the device is on, voltage drop is very very negligible. We can't say zero, but it is almost very small. I don't know, it is 1 volt or 1.5 volt, like that. It is very small. Now, when you compare to the load and all or source, it is very negligible. You can neglect that also. Similarly, when the device does not conduct, means off state, then it acts as a infinite impedance. What is meaning in that? When the device is off state, automatically it acts as a open. That's why I mentioned here as a infinite impedance. So when the device is on, it will be drop will be very very minimum voltage drop, because it is in the ideal case the device is on, means switch is closed, then automatically voltage drop across that will be negligible amount. Similarly, when the device is off state, means it won't allow any current pass through that. No, that's why we call it as a infinite impedance. Switches are in power electronics converters, on and off helps to convert power. All the control strategy, whether AC to DC or DC to DC means chopper, DC to AC is inverter, AC to AC is AC voltage controller, and different frequencies we can able to operate. The switch mode power converters gives higher efficiency. That's what buck converter, boost converter, and buck boost converter and all. Anyhow, that is also there in our syllabus later in it. That is all, switched mode power push pull amplifier and half or full controller, or also you can say that flyback converters. All switched mode power. There is a lot of different is there. Normal linear regulators and then switched mode converter. These are the very efficient all systems and all we are using that. But due to the non-linearity, one drawback is there. Any controller, once if you are using semiconductor devices, that leads the one of the major drawback in that is a harmonics generation in the source side as well as the load side. So filtering requirement is more. Otherwise, every component will inject the harmonics to the lines. That is the huge problem in the dispatch center. So there is a low dispatch centers are there, no? National dispatch center, I mean state dispatch center, and then national wise dispatch center or central dispatch center. So what they will do is they will monitor that power, all the compensations, what is our reactive power requirement and voltage levels, all the things they will monitor and they will compensate the requirement. But if harmonics or everybody is injecting to the lines, the compensation is a difficult task. That's why in non-linear loads we use, preferably we'll use as a capacitor banks. Even many industries will use that capacitor bank, automatic switchings and all. There itself they will compensate. The reason is very straightforward. In the billing process, I think I already mentioned in the earlier introduction class itself. Normally, when you are consuming power in terms of the units in a house and all, you can see that kilowatt hour billing. But now if we come to industry or maybe colleges and all, they won't bill that kilowatt hour. So they will use as a KVA billing. The difference is there is a factor, power factor. So now one thing. Suppose if you are operating as a very lagging loads or a low power factor operations, if you do, they have to compensate in the dispatch center. For that, they will charge more. Instead of kilowatt hour billing, if they use KVA billing, KVA hour, then what you can write kVA into power factor will give the kilowatt. So instead of charging their units, if they charge the kVA, if you are operating as a low power factor, you can see that instead of 1, if it is power factor is 1 kVA and kilowatt is same. But if you are operating as a zero point 0.8 or 0.7 or 0.9, little bit lower operation, then you can see that kVA is nothing but a kilowatt by power factor. So that itself will increase the value of kVA. Once if you are increasing the value of kVA, that's a formula is everybody is known. kVA is nothing but a kilowatt by power factor. But normally if it is unity power factor, what will happen? Kilowatt or kVA billing is fine. But now suppose if you are operating some load, any particular load, in that case there is a 100 units we are consuming with 0.8 power factor. Then what will happen? You have to pay 125 units. You can see that 100 divided by 0.8, let's assume, or if it is still less, it will increase more. So 125 kV, they will 125 into price. Otherwise if it is unity power factor, 100 into price. Now you can see that the difference. So that is the reason the billing department, means electricity board, are using as a kVA. So if you because we need to do more for you in the dispatch center, you are injecting the more harmonics or you are operating on low power factor, they have to compensate that, they need to spend some money. That's the reason they will collect from you. That's what in industry or in any huge sector, they will use as a capacitor banks in the our substation level, in our college substation level, and they will compensate here itself, they will improve the power factor. So that is the major factor we need to consider. But houses and all little bit small rating load, they don't much consider in that. But if we go for as a three-phase load and all are high rating loads, obviously all the equipments are nowadays non-linear load, that leads the problem. So that's what the problem in this harmonics and all. Now we'll see the applications. The heating, light control, fan control, and DC to DC drive control, and AC and DC power supplies, electromechanical process, static wear compensation, this is compensation, active harmonic filters. So for all these things we required as a switches. Although cost of the device in power electronic equipment may be hardly exceeds 20 to 30%. Now we can see the logic in this sentence. Normally if you are using as a very efficient switching device, comparatively normal devices, that cost may be 20 to 30%. But once if you are using that equipment in our controller, that performance wise it will influence more, that impact will be not considerable for the 20 to 30% of the total equipment cost. So that is the performance or characteristics of the device will be better. That's the reason we can able to use high performance switches in that our application. Now we can see that classifications of a semiconductor devices. There is a power semiconductor device, we can classify two terminal device and three terminal devices. What are the two terminal devices? Like if you consider diode, what is the diode? Anode and cathode. So that's why it is a two-terminal device. And Schottky diodes, this is one of the type of diode. It is advantage compared to the normal. Of course, there is a disadvantage also will be there in terms of the rating and all. We'll see that anyhow. So now, three-terminal devices. There is a BJT is a three-terminal device, and then base, emitter, and collector, and then power MOSFET, drain, source, gate, like that. So we have IGBTs, collector, emitter, gate. So these are the some of the devices we have in a power semiconductor devices, two-terminal device as well as the three-terminal device. Anyhow, SCR is known to you. That is a thyristor. So these are the one of the classification. And another classification you can see based on the control, whether it is a current control device or voltage control device. So in a current control device, you can see BJT is a current control device. As I said, once current is passed through the base of that BJT, automatically device is going to be turned on. And if you remove the current, device is going to be turned off. So that is the reason we can say that this is a current control device. Even SCR also current control device. So because we are passing the gate current, it is going to be turn on the device. So here these devices are the current control devices, and GTO also current control device. And now there is a voltage control devices are MOSFET is voltage control device, and IGBT is also voltage control device. A mass control thyristor MCT, that is also voltage control device. So I think this will not be there in the syllabus. So these are the devices we need to discuss. One is a diode, then BJT, then anyhow SCR core, and MOSFET IGBT. So one device is one class. We'll see that we have only three BJT, MOSFET, and IGBT and comparisons. So these are the same two-terminal device and three-terminal device classification. Now we'll see the power diodes. Now here the different is, as said in the earlier, the normal diode is different with that power diode. One region is going to be add, that is a minus N region or a drift region, and why we need to add, and these things we'll discuss. So there is a diode, bipolar static switch device. It has two layers, P and N materials. The layers from a junction called PN junction. So like P layer and N layer, and in between there is a junction, it is a PN junction. So if this comparatively what you call it as general purpose diodes, there is a power diodes are complicated in structure. The reason is we added intentionally, we are adding as a one layer there, and the operating characteristics also low power than the low power general purpose diodes. So this will be little bit different, and power diodes are constructed with N minus one layer, N minus layer, that is a drift region in between anode and cathode. So normal diodes and all anode and cathode will be there. In between anode and cathode, we are adding as a one more layer, that we call it as a drift region between anode and cathode. These diodes high forward current carrying capability and high reverse blocking voltage, breakdown voltage, reverse breakdown. Now this is advantage normally. So if any device is there, when you are operating the device in a circuit, what is that function? Normally, either it has to be on or it has to be off. But what I want to do is the device is going to be on, it has to carry the more current. That is only our purpose. The device, the current carrying capability or rating of the device must be more to meet the low demands. That's why if you are using as a power diodes, that can capable to carry the forward current. So current is going to be carry that will be as a forward current. So it carry the high current, and also you can see that reverse breakdown voltage. As I said, now in the case of SCR also, if you apply reverse voltage, in the reason behind this is when you are using as any equipment in a device, when it is in the off state, there is a possible to get as a reverse voltage applied across the device. If that voltage is within the limits, then it won't happen. but if it is beyond the specified, automatically the device is also going to be on. But that should not be. Only whenever you require it has to be on, because of in the device circuit operation, some device may be conducting, that voltage will make applied across this device, and that voltage may be higher than that breakover voltage, then automatically device is going to be triggered. But at that instant we don't want to trigger the device. So that's why what we need to do is we have to provide the breakdown voltage is high, so that we can use the devices in the operation, even high rating of applications also, even if it get the higher voltage, but obviously that voltage must be less than the reverse breakover voltage only. Otherwise it will be turned. So that's why if the capability itself is more, then it can withstand in that circumstances. And area of PN junction in a power diode is much high. So compared to the low power diode, if area is more, automatically carrying capability also will be more. So now we'll see the structure of that. There is a normal, P and N. So this is the structure of a power diode. Now you can see that is symbol. First one is the symbol, anode and cathode. Let it be in this diode case, you may be aware that whenever anode is positive with respect to cathode, so anode is positive with respect to cathode, automatically device is going to be conduct. Instead of saying as a forward bias, you can say directly as a conduct, because in the case of SCR you can't say that. SCR is first will be forward bias, that must be always required to trigger the SCR. So anode is positive with respect to cathode, that will be as a forward bias only in case of SCR, but it is not conducting state. To conduct we required as a gate pulses or a current or a voltage. So that's what, but whereas here you can see that directly it is going to be conduct. Now, as I said, there is a P and N only, our what you call it as layers. But now there is a N minus layer or a drift region we need to introduce. So that's why you can see that there is a heavily doped, means high conductive material. So the P layer is heavily doped, and I mean P plus as well as N minus also heavily doped. But N minus, I mean N plus both are heavily doped, and N minus we made it as a lightly doped material. So we are sandwiching that to in between the P plus and N plus. Then we call it as a another region, that is a drift region will be formed, that will be as a lightly doped. Now you can see this sentence: any junction having highly doped layers on both sides. In the junction you can see that P plus and what you call it as N minus, if it is both are highly doped, it requires lesser breakover voltage. To turn on this, we required only less breakover voltage. But whereas in our case, you can see that one side is the lightly doped, and it requires a higher breakdown voltage, because this P plus is heavily doped, but another side there is N minus is a lightly doped, then we required a higher breakdown voltage. So here intentionally added lightly doped N minus 1 layer in between highly doped layer to increase the voltage blocking capability of the diode. That is our purpose, to improve voltage blocking capability, in the sense device must be withstand even if that voltage is a little bit higher. That value decided by what we call it as our breakdown voltage, how much it can withstand. Based on that, the area and all we can decide. Now width of that also will decide. Now you can see that significance of the drift region. So why the drift region? One thing we noticed at this point, you can see that intentionally we added N minus 1 layer between these two. and that will increase the voltage blocking capability. That is one of the advantage. Now, anode is made negative with respect to cathode, then the depletion layer across the junction, the depletion layer uh, penetrate more deeper into n minus 1 layer in order to equalize the charge on both sides of the junction. So that is one of the concept here. If you do that, that way we can able to n minus 1 layer to equalize the charges. So in this, increase the thickness of the depletion layer. Then what is the advantage by increasing the thickness of a depletion layer? So that will be reverse blocking capability of the diode. So it will increase the thickness. That means this will increase the thickness of the depletion layer. Automatically blocking capability of the diode will increase. One thing also we noticed in case of SCR, whenever if your voltage, applied voltage is inversely proportional to the thickness of that thing. So if you are increasing gradually voltage, and then that junction is going to be breaks down. So that is only the higher thicknesses of the n minus 1 layer, higher the reverse blocking capability. So if we are thickness are more, means we required more voltage to break that junction. Nothing is more than that. So just if the thickness is more, we required more voltage to break the junction. The maximum thickness of the depletion layer, n minus 1 layer, decides the reverse blocking capability of the diode. So if the thickness is more, obviously blocking capability, reverse blocking capability of the device or a diode will be the more. The signal diode, that means normal diode, will block small voltage, whereas power diode will block large voltage because of the additional intentional n minus 1 drift region. So there is a power diode should operate in several kiloamperes. You can see the comparison wise also. This will be 7 kiloamperes of current during conduction in forward bias conduction with low power losses. So here also this sentence low power loss means that even though you are capable to carry that more current, but while you are operating the device, it can take care of that how much conduction. So that we can say that current rating in the forward bias and power loss. So power dissipation is taking place, that is in the terms of a power loss. So that's why we can see that how much power loss is going to take place during on condition, during off condition, or under on process. All these things will comes under switching also. That's what the dynamic. And block high voltage about several kilovolts in the reverse bias condition. For the large blocking voltage, the width of the depletion layer must be large in order to limit the electric field strength. So lightly doped PN junction provides high resistance during forward bias condition. Consequently, during conduction, a large power dissipation with diodes, you can see that a large power dissipation is taking place during conduction. That will be fine, not the on position or off position during conduction. This sentence is important. During conduction case, we noticed in case of SCR also, power loss will be more, but once completely on or completely off, then power loss will be minimum. What is the reason? Because if the device is completely on, then the voltage will be minute, loss is, voltage drop across that will be nearly zero or very, very small. Then the current may be large, but if your power is multiply that to, power loss will be minimum. Similarly, when the device is open also, it won't happen much problem. And during open, then what will happen? Voltage and current during open condition or during on condition, both will be present. That's why you can get it as a losses are little bit more during the instance. Now, to sort out this problem, lightly doped n-1 layer is introduced between the two highly doped p plus and n plus layers. That's why we use it as a n-1 only. So that will thickness of that layer depends upon the breakdown voltage of the diode. Higher breakdown voltage means obviously what will happen? This drift region will be wide, means more. So then the drift region is absent in low power signal diodes. So whereas normal diodes, whatever we are using in the low rating applications, there we don't have as a drift region. So it is having as a anode and cathode only, P and N. Now let us see the what will happen when the power diode is forward biased. So normally in case of ordinary diode also, once it is forward biased, it starts conducting because we don't require any gate here. Only in the power case there is an advantage. Under this condition, holes will be injected from P plus region into the drift region. So where is that P plus region? Anode side, there is a, this one will be P plus and there is a N minus drift region, and this side you can say that N plus. So that means we can see that holes will be injected from the P plus region into the drift region, and some of the holes with the electrons, so that will be companion with the electrons in the drift region. Then the injected holes are large, they attract the electrons from the n plus 1 layer. So this one will be near to that n minus 1 because in between we placed that. So then what will happen if we, that holes will be injected and electrons will be attracted? Holes and electrons are injected into drift region simultaneously. As you can see this. So there is a, this side will be injecting and this side will be injecting, then automatically holes and electrons are injected into the drift region simultaneously. Hence the resistance of the drift region is reduced significantly. Normal case, when if it is not in the operation, the drift region resistance will be high. But whereas if you are operating that in the circuit, if the drift region resistance is high, then already device will conduct now to trigger the, to operate the switch, the device has to be on. Once the device is on, but drift region is more resistance, then power dissipation will take the problem. So that's why what they will do is, we are under operation condition, drift region impedance we can reduce. So a large amount or significantly we can reduce that. Current goes on increasing, but drift region resistance remain almost constant. Under operating condition, drift region resistance will be maintained constant, but current goes to on, or current will be increases because the device is on. Hence, on state classes in a diode are reduced. This is what we required also. Under on state, time duration is more. No, when we are operating, it will take more time to continue to conduct the some instant. But whereas if you are keeping that resistance is continuously throughout the on operation, you are getting as a less voltage. So that's why what we are doing is you have to reduce that on state power losses. So if you do that mechanism, it will be reduced. This phenomena is called as a conductivity modulation of a drift region. And this phenomena is present in the almost all the power devices, whether you go for BJT, power, all terms are BJT, to call it as power BJT, power MOSFET, power IGBT, like that. So you can able to make use of this phenomena to reduce the drift region resistance. So now this phenomena is present in almost means BJT as well as the MOSFET, IGBT and all, they will use this. So this is the VI characteristics of a power diode. So normally you can see that P plus and N plus layers will be there. In between we make use of a N minus 1 layer or a drift region. Now you can see the symbol. What is the symbol? This line you can remember in our labs also, diodes, all these things are available. You just take it and try to identify anode, cathode, and this case we can see that anode and cathode will be there. This will be anode and this side will be cathode. This small strip represent that side is a anode side. So I mean cathode. This one is a cathode and anode and cathode. So now we can see there is a operating as a switch or operating as or on state or off state, straightforward. We can see that anode is positive with respect to cathode. Then what will happen? This is starts conducting. So the anode is positive with respect to cathode, then switch will be closed. It is going to be conduct. And similarly, in this case, you can see that anode is negative and cathode is positive. So even though if it is a forward bias, but to make this on, we required small amount of voltage. Anyhow, if that breakdown voltage is happened, the forward junction potential, if it is high, then some specified limits, then automatically this will be conducting. So this is the one thing. And reverse side breakover voltage is always less than that specified. For that reason, we make use of to identify a reverse breakdown voltage within the specified limit. So this is the now we can see small operation diode only. Normally we can forward bias condition what will happen and reverse bias what will happen. So there is a p type layer and then n type layer. So to turn on that BJT or maybe in the diode, what will happen? The junction has to be breakdown. To break that junction, we require to apply some forward voltage. If forward voltage is applied, then the junction is going to be breaks down. But whereas in the gate, we are in the case of SCR, we are passing as a gate current. So now you can see this dynamic switching characteristics of a diode. So power diode. So we can see in the case of dynamic characteristics of SCR also we noticed under off process and all reverse recovery time and gate recovery time. Then the total time is sum of the reverse recovery time and gate recovery time in case of SCR. But here we don't have gate terminal here. We divided that interval two parts. So one part is from 0 point to the maximum reverse recovery current to the maximum. You can see this. There we divided two parts. This instant of 0 forward current to maximum current, and then IB current from maximum to 25% of the rated current. So during this instant, we can see that losses and all. So initially, anyhow, I will show that theory part also I added. There is a forward current because the device is on under on state. I am telling device is on, it will carry some current. So let it be load current or whatever current you want to apply to that particular device. There is a current and you have to initiate that process. Then the reverse voltage applied across that, the current will reaches 0 and then it will develop in the negative, and that values we can say that TB and TR, sum of these two TA plus TB will give as a TRR. That will be as a maximum reverse recovery time. And now there is a charge also will be there, but we can see that voltage when the device is on state, voltage drop across the device we are significantly will represent, but it is very very small. Even if you write like this, x-axis itself is a correct, but we must use that in the thing. So now we can see VF voltage drop across that when the device is conducting state, drop is only 1 volt or 1.5 volt, very small, and that we are representing. Now we'll see the dynamic characteristics when the diode is conducting. To turn it off, a reverse voltage is applied. So let it be diode is automatically conduct when anode is positive with respect to the cathode with voltage of small voltage, let it be 0.6 or 0.7 volts, then automatically the diode is going to be conduct. When the diode is conducting, and what will happen to turn off that, we need to reverse voltage need to apply. The diode current momentarily becomes negative before becoming as a turn off. So completely before becoming 0, we are completely turn off, or you can say that negative current will be developed. When the reverse voltage is applied, the forward diode current decreases linearly to the 0. So once any device, the reverse voltage applied across the device is going to be trigger. So that the fashion, but it is undesirable to operate under fourth quadrant operation in the SCR case and all. So that's the reason generally we don't use to trigger that in the quadrant operation. Now, when the reverse voltage is applied, forward diode current is decreases linearly to the 0. Diode continue to conduct in the reverse direction, because why it is continue to conduct, like example of fan, even switched off it will continue to rotate some more time. Same manner, the charge particles, as I shown you in the animation, there is a charge particles are present, so that will be because of that it will continue to conduct some more duration. So the direction, because of the presence of a stored charge in the two layers. So that is the reason. Now the reverse current flows for a time called reverse recovery time, TRR. So the reverse current is flowing through that, will considered as a reverse recovery time. It is usually less than the 1 microseconds. You may be shown in the diagrammatically, it is a little bit bigger diagram and we are showing as some gap, but strictly speaking, normally the device is going to be turned off when reverse voltage is applied across the device. So that we call it as a reverse recovery time. It will be less than 1 microseconds of time. And TRR consists of two stages, as I said, TA and TB, and some of these two will consider as a TRR. So TB and TA, we can see that zero crossing of that, when the instant reaches the 0 point, from there onwards forward current and peak reverse current, IRRM. So maximum or a peak reverse current. So that is I reverse or peak reverse repeated current. So you can see that under reverse bias condition, that current will be appear across that. So that will be developed up to the maximum. So during this, the charge stored in a depletion layer is going to be removed. Our intention is to remove that. So that is what we applied as a reverse voltage applied across the device. So in that, TB is the time between the instants of IRRM to the instant where the 25 percentage of the IRRM is reached. That is a, we call it as a TB. During this time, charge from the two semiconductor layers is removed. So completely whatever the charges are present in that inside, that is going to be removed by this process, recombination process. Or also you can say that reverse voltage applied across the device, that is going to be turn off with a specified amount of time. It is very minute, even you can neglect, but there is a time is required to remove. I said that 1 microseconds of time to remove that. No, similarly to turn on or to turn off, we required as some instance. So the reverse recovery charge, that is a QRR, reverse recovery charge, must be removing during TRR. So that charge also going to be removed. As thumb rule, the lower TRR is faster the diode can be switched. Now during TRR time, that is the reverse recovery time, the QR must be removed. Anyhow, I mentioned that in the previous sentence. The value of QR can be expressed as a half into IRR maximum into TA plus TB. So you can take it as a common of half into TRR. That will give as a half TRR into IRR. So that will be peak reverse current, that is IRR in terms of QRR and IRR is equal to, so there is a relation 2Q by TRR, and then peak reverse current, that is a IRR, can be expressed in terms of dI by dt and dA by TA, and its value is equal. So now IRR you can represent TA. This is empirical relation. We made that IRR is equal to TA into di by dt, and equation 1 and 2 both are IRR, and equate it to that, and you'll get it as TRR into TA is equal to 2Q by di by dt. That is a current. So now we can see that why that ITV is very small compared to that, because another one is a high magnitude intensity, but once that reaches the maximum, there onwards dissipation is taking place. In that case, once the dissipation is 25%, density of that will be minimum and it sharply decreases. That's the reason. And from that, TRR square is equal to of this, and we'll get TRR is root of this. So this will be as a small compared to the TA and TRR. And the time ratio TB by TA is called the softness factor or S factor. So why? Because this TRR, the ratio TA and TB by TA is called a softness factor. Now we can see that S factor determines the voltage transients when the diode removes its original state from on state to off state. Usually its value is equal to unity. So that's softness. But if S is 1, the reverse recovery process of diode have low oscillatory. But if it is a less than 1, then the reverse recovery process of diode contain large oscillatory voltage, over voltage. And according to the reverse characteristics, diodes have classified as a fast recovery, and then diodes are soft recovery. Based on the recovery, you can see that S value, according to the recovery characteristics, diodes are classified fast recovery as well as the soft recovery. You can see that fast recovery means S is less than 1. You can see this, if S is less than 1, and then soft recovery S is equal to 1. And in this we can see that S is less than 1, diode is called as a fast recovery, is equal to 1 is a soft recovery. Reverse recovery time, that is a TRR of a general purpose diode, is large and its value is 25 microseconds. So recovering time is large means the value of the device will be cheaper. So we are using as a high recovery time. For that they will charge you the high cost. That value is 25 microseconds. General purpose diode, its recovery time 25 microsecond, and fast recovery diode is small and its value is 25 nanoseconds to 100 nanoseconds. So it is very small when compared to that. So this is the soft recovery, and then abrupt recovery. Soft recovery smoothly is going to be turned off, but abrupt recovery, there is spikes will be getting, even though the TRR value is a less. That we call it as a abrupt recovery. Now diode reverse recovery process with various softness factors we will show like this. So that will be as a maximum peak is IRR, and then here minimum peak is not a 0.25 R into IRR. Now there is a types of power diodes. Then one is a general purpose power diode, another one is a fast recovery diodes, and third one is a Schottky diodes. So these are the three types of diode. This is also an important question. Explain types of power diodes. All the three you can mention. So now we'll see the general purpose diodes handle powers at main frequencies, that is a 50 Hz frequency, or up to below 1 kHz operations we can use as a general purpose diode. So on state drop of this type of diodes are low as possible. So on state drops will be minimum, but its turn off switching time is more. So turn off switching time is more, then automatically we have to wait until this device is going to be turned off completely. Otherwise what will happen, the other device we cannot operate. Once if it is turned off, only we can able to operate. So this is achieved with the this is achieved with the help of increasing the doping level, and therefore reverse recovery time is large, about 25 microseconds. And the rating of general purpose diodes 1 ampere and 50 volts to 5 kilo amperes to 100 kilovolts. So these diodes are used in the rectifiers and converters. So the rectifier is a I don't know as a feedback diodes, or you can say that freewheeling diodes, like that we make use of that. And fast recovery diodes, the reverse recovery time is order of 25 to 100 nanoseconds. That is a fast reverse recovery time. Because of that only we call it as a fast recovery diodes. And they consist of highly doped p layer and then n plus layer sandwich in by lightly doped n minus 1 layer. So by doing that clubbing, we in between that there is n minus 1 layer is placed in between the highly doped layer n plus and p plus layers, and thickness of n minus layer is increased to increase the voltage blocking capability that we observed in the structure case. And TRR is reduced by reducing the storage charge. If we know that is TRR is decided by how much it is going to be stored. If it is stored more, to dissipate that it will take more time. That's what. And now this sentence will clear that problem. TRR is reducing the storage charge in the neutral region. That is a and minimizing the carries the lifetime. So less charges it will recover charge first. So this is achieved by forming the recombination neutral region. And in very high frequency applications, p and n diodes are used. Means p-n junction, or you can say that fast recovery diodes are rating is 1 ampere to 50 volts and 1 kilo amperes through 3 kilovolts with reverse recovery time less than 55 microseconds. So applications, you can see that these type of diodes, the inverters we can use, then choppers we can use it, and another one is SMPS, and then UPS, uninterruptible power supply, and resonant converter. So for these applications we can use as a fast recovery diode. And last one we can see that Schottky diode. So this is the one small difference, nothing is there, that junction we are removing, nothing else. Because of that junction it will take some time to some voltage and all, no, very small, or you can say that. That's why when you compare the characteristics of Schottky diode and then PN diode, we required, some voltage to break the junction. So this voltage is 0.6 or 0.7 voltage. So now to trigger this, we require some voltage because of that junction. If you remove that junction, automatically it starts conducting. So very sharply it is going to be conduct. So this is the difference of these two things. Very small directly metal you can attach, and that it in the Schottky diode, the voltage you can see that drop, it is only 0.2 volts is required to conduct. But whereas here in the PN diode we required a little bit 0.7 something voltage is required to trigger that, but we required only 0.2 voltage in the Schottky diodes. Very low cutoff or cut-in voltage to break that junction, or you can say that obviously you can say that no junction at all, but it will require very minute of voltage to trigger that Schottky diode. So reverse breakdown voltage of the diode is only 50 volts when compared to the 150 volts of a general diodes. And this PN junction is eliminated. So if the two materials, P layer and N layer, that will form as a PN junction. Now what we are doing, PN junction is eliminated directly. A thin film of metal is placed directly on the semiconductor. You can see that there is a just metal you placed on that, it will remove that junction, or you can say that. Normally aluminum is deposited on N-type semiconductor. The metal is anode and semiconductor is a cathode. We can use it. So now since there is no PN junction, the storage time is absent. So because what will happen, because of that junction it will store some charge particles. To remove that we require, hence the turn off time is absent. So now the turn off time will be absent. Hence the Schottky diodes have high switching frequency, because very small turn off time is not there, means switching frequency very faster rate it is going to be on and off. This will be used for high switching frequency operations. Drift region is also absent, and so on state loss is very low, and but the large reverse leakage current will be present. So there is a some applications we can see that switched mode power supplies we can use it in this Schottky diode application, and AC to DC converters we can use it, radar systems, and then mixers, and then detectors in the communication circuits we can use this, and then feedback and freewheeling operations of power converters we can use it. So these are the some of the applications of Schottky, and applications of power diodes. You can use the uncontrolled rectifier, that is everybody known, you know. Controlled rectifier means power electron, uncontrolled means diode rectifier, that is half wave or full wave or bridge rectifier and all. Uncontrolled rectifiers, and feedback or freewheeling operation in our phase control rectifiers or choppers or inverter. When RL load is there, to freewheels that we can use as a feedback diodes. Almost all communication circuit for SCRs used power diodes we can use that, and half control converters and half bridge converters. This in inverter case there is a feedback. Nowadays all latest devices inbuilt diode is getting, so that is not a matter. And rating of power diodes, so that we'll see in the next class. I think time over. So we'll see. I think maybe tomorrow I will take that second hour as well as the last hour, 3:30, 6th hour free. I think I will take that 6th hour also on Friday. 2 hours I will take. Okay, if you have any doubt, you can ask me. Otherwise, you can leave. Attendance is very poor. Try to maintain attendance.